He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Any sort of exposure to, the fun and interesting things that people are working on and figuring out ways to articulate some of the ridiculous things that we're doing. It's such a really valuable experience,
Kia ora, nau mai haramai ki te ao hurihanga. Hello and welcome to Our Changing World. Ko klekin kanan tēnei. Last week, we introduced you to the Australian Synchrotron, a massive structure in a Melbourne suburb designed to produce intense beams of light for use in science. We also poked our heads into some of the X-ray beamlines. That's the name for the research area where the scientists go and shine light on their samples to learn what some people are studying there. And turns out, as physics master student Kane Hill is also learning, it's a huge range of things. Now, while there are a lot of different X-ray beamlines here, the light made in the synchrotron spans from gamma-ray light through X-ray, ultraviolet, visible, down to infrared light. Infrared is the light given off by warm things, which is how night vision goggles work. It's also used in your TV remote. Next up is microwaves, which you'll have heard of. So there's a portion of the infrared band of light, the bit that backs onto microwaves, that's called terahertz. And that's where we're hanging out today.
Terahertz is itself a really interesting field. It's sort of an area that hasn't been, it's relatively new in terms of how much people have been able to look into things, and it would be really necessary for a lot of areas in the future.
The name terahertz is related to the frequency of the light waves. Tera is just one of those prefixes used because otherwise the numbers are annoyingly big. So just as kilo means 1,000, tera means 1,000,000,000,000. And hertz is the unit of frequency. So for terahertz light, you have 1,000,000,000,000 light waves passing a particular point each second. For his master's, Kane did research using terahertz light, which is why he got invited on this trip to the synchrotron with his University of Auckland colleague, Dr. Freddie Leiswa. He'll write it up as part of his master's course, so he's here to learn, help out with the research, meet scientists from all over, and really just soak it all in. We're catching up on a picnic bench on the synchrotron campus, just outside the guest house, where visiting researchers stay. Now, Kane would have used a source of terahertz light, or radiation as he calls it, in the lab in Auckland for his work. But synchrotron light is a totally different beast.
One of the biggest things with terahertz that people have been trying to fix for years and years is trying to find really high-powered sources of terahertz radiation, because terahertz radiation is all around us. Anything that has warmth to it will be emitting terahertz radiation. We emit terahertz radiation all the time. The only issue is that we can't really do anything with that because it's all over the place and there's no structure to it. But at the synchrotron, we have access to this sort of very high power and then wide range of terahertz frequencies that can be quite difficult to get otherwise. And so it's really interesting to see, the ways that materials might react or various technologies we're developing.
And why do we need it? What are those future areas that terahertz might be important for?
One example people often talk about is wireless communication. So currently at 5G, which works at quite a high microwave level. And then terahertz is the sort of frequency band above that. If we wanted to move to 6G, we'd have to develop technologies that would work in a terahertz space. The challenges, the obstacles, the hurdles with that would be that, at different frequency ranges, materials can behave differently. And so we can have sort of effects that we're not used to dealing with at lower frequencies or at higher frequencies. Hence why it's so important that we need to develop terahertz technology.
By terahertz technology here, he means the ability to make, manipulate, and detect terahertz light, so you can properly test materials for this new frontier of communication and computing. It's kind of like terahertz was the forgotten cousin of the light family for quite some time, though now there's a bit more going on. These days, it's being used in some airport security because it's harmless, but it can penetrate things like fabrics and wood, and it's also used in car painting, where it helps determine the thickness and evenness of paint without touching it. In research, people are investigating its use in medical diagnosis, and here in the synchrotron, Terahertz spectroscopy is being used by many researchers who want to really get to know the crystal or material they've made. People like Nicholas Page.
Do you remember that paper on extrasolar activity I published?
Oh, wait, sorry. That's Nicholas Cage, who actually has also been to the Australian Synchrotron. This is from the 2009 film Knowing. In the clip, he runs purposefully past the impressive mountain of stainless steel that's one of the X-ray beamlines, up the stairs with a neat view of the synchrotron in the background, and then rattles on about solar flares and the end of the world.
A 100 microtesla wave of radiation that would destroy our ozone layer, killing every living organism on the planet.
The place does make a cool background for some good old-fashioned sci-fi. But I meant Nicholas Page. Born and bred in Dunedin and now a PhD candidate at the University of Otago. And someone who, right now, is just very much looking forward to getting some sleep. His beam time, a total of 3 full 24-hour days, started 2 days ago.
And I've been working long hours since then. You get a certain amount of hours, doesn't stop overnight, so...
We're chatting in the terahertz beamline office space as one of his samples is getting analysed. He's gearing up for another long night of research.
This is basically my last huzzah for results before knuckling down and sort of getting everything sort of written up.
What is the focus of your PhD?
I work with metal organic frameworks and basically looking at designing, making and synthesising new metal organic frameworks and trying to learn about their properties and what sort of applications and potential applications from that.
Okay, metal organic framework.
Yes.
What is that?
All right, so whenever I catch up with extended family and things like that, they always want to know what you've been working on, what you've been doing. So probably the best explanation I've found is there used to be these toys people used to have, which were basically a set of magnetic balls and sticks and stuff like that. And when you're a kid, it's really fun. You could basically use magnetism to basically assemble sort of like all these cool sort of structures and things like that. And metal organic frameworks are somewhat, I think of them as somewhat similar. You can choose your organic linker and your metal basically sphere, and you can heat them up and they will assemble and crystallize into various frameworks. And what very interesting about metal organic frameworks is that they have very large porous volumes in them with large surface areas as well, and that can give rise to many sort of fascinating, interesting applications, particularly things like gas storage.
This is one of the ways that we might be able to use MOFs is to store, say, hydrogen, carbon dioxide?
Yes,
is that what you're talking about?
These are sort of the two main gases, as well as nitrogen as well, that is of very keen interest in MOF chemists.
MOFs is a much catchier term than metal organic frameworks, and it's what people working with them generally say. But the full name is helpful. The metal part is a metal ion. Some have zinc or iron or copper in them. And then the organic linker is the chemistry interpretation of the word organic, which means a linker that has carbon in it. Now, think about that magnetic ball and stick game. If you change the size or shape of the ball, or the length of the sticks, if you vary all these things, then you can make all kinds of different shapes. And then you repeat this shape over and over to get a crystal. But it's not fully solid. It's like a regularly shaped crystal sponge. And MOF researchers are super excited about these pores in the sponge because we need clever solutions for capturing carbon dioxide out of the air and for neatly storing hydrogen gas so we can use it as a clean energy fuel. So one of the key things to find out about your MOF is how much of your gas of interest it can hold.
We work with a collaborator for taking these sort of gas absorption measurements. The way we've found it's a lot easier to synthesize your MOFs first, get all the sort of hiccups with that sorted out, get your sort of structures synthesized first, and then see what they can do.
And we're sitting in the little office outside of a beamline in the Australian Synchrotron.
Yes.
So specifically, what are you doing here?
So what I'm doing here is I'm trying to measure the very low frequency vibrational modes of my MOFs. So one of the key things to sort of start to learn about metal organic frameworks is that they're not sort of very sort of static, rigid crystals. Everything's sort of vibrating, everything's in motion. So that's what we're doing here. Is I have brought across a whole bunch of samples of my MOFs, have different solvents in the pores of them, heating them up to basically evacuate the solvent out of the pores of the framework, and then measuring how these vibrational modes will change as a response to temperature.
So you've got each atom vibrating across 3 dimensions, and they make up molecules, which are also vibrating. And then when you zoom out to the crystal structure, you've got different ways the whole thing can vibrate. Think like bricks, and then a wall, and then a building, vibrating in an earthquake. The terahertz light is really good for giving information about this whole thing vibration.
So at the start of the process of making a MOF, one of the first things you do is you grow crystals of them to collect the crystal structure. That crystal structure is under very sort of specific conditions. Basically, it's just been sort of inside the pores of the MOF will be the solvent that you've used for your synthesis and stuff like that. So the crystal can change as you're sort of putting it under sort of different conditions and stuff like that.
So is this like you're more like testing it in the real world?
Yes, that's a very sort of good way to put it. Yeah.
Kind of pressure testing it and seeing,
Yep.
okay, well, what happens when we heat it up? What happens when we get rid of the solvent from the pores?
When we're heating it up, are we sort of seeing that the crystal's starting to fall apart as well? Are we sort of seeing it sort of start to vanish?
Nick is in Australia for a month in total. He's got one last night on this terahertz beamline, then he's going to head to the city for a few days, mostly to catch up on sleep, and then back to the synchrotron to go to a different beamline, one that will help him understand the crystal structure of some other MOF samples he has. After that, he's got one more stop.
And then I am flying up to Sydney to work in our collaborators' lab there, running some of the gas storage measurements for 2 weeks.
And then back to Dunedin.
Yep, and then back to Dunedin.
We've moved now into the beamline room, and Nick has assumed the position in front of the computer and the bank of monitors, keeping an eye on his results.
And this is your day.
This is, yep,
/ night /
yep.
many days.
Yeah, I mean, I don't actually need to be, while I was doing this, I don't need to be present. I can go consume as much coffee as I can reasonably stomach.
It's late in the evening, and he's planning to maximise his remaining time before the 9 a.m. changeover. The next team on the beamline is also representing Aotearoa New Zealand. Kane, who you've already met, his University of Auckland colleague, Dr. Freddie Laiswa, and Kitty Van Conant from Victoria University of Wellington. But they can't get stuck in straight away. There's a bit of bespoke beamline work that has to happen first. That's a job for senior beamline scientist Dr. Dom Apadou, because this terahertz beamline is really his domain. And he's pretty passionate about his job.
What gets me out of bed in the morning is the technical side, is one aspect that really gets me going, always trying to improve. And also the other aspect that really gets me going is the interaction with the users. That for me is priceless, because this is where ideas float and things burgeon and grow into flowers and trees or whatever.
Now, Nick wanted to heat things up, but this next group, well, they want to cool their samples way down.
They place the samples on a piece of metal, which is then exposed to the cold environment, where the samples can then be cooled down to about 6 Kelvin. Yeah. So this allows them to do a whole bunch of studies.
And when you say 6 Kelvin, what's that in Celsius?
So that's about minus 270, 60, 70 degrees Celsius. Yeah. Way cold.
Very cold.
Yes, way cold. So we have this is called a closed loop cryostat. It's basically a refrigerator, if you want. It works like a refrigerator. It's filled with helium gas, and it takes about 5 hours to cool down. I'm just about to load it up on the spectrometer right now.
The cryo chamber that's going to do the cooling is a bulky, heavy-looking piece of machinery. Dom uses a crane to lift it in place on the spectrometer. A large L-shaped machine that spans most of the room. This is the device that detects and analyses the interaction of the sample with the terahertz light. This is a big part of Dom's job. making sure that the beamline is ready for what the users want to investigate.
So before they apply, we have an exchange where we discuss their experimental requirements. The first thing is it feasible? Is it sensible? Are there potentially other techniques that would be more useful? Once we come to an agreement that this is the right technique, then we go on to move on to, well, what are your requirements for the sample handling? Is it ambient? Is it pressure? Is it high temperature? Is it cold temperature? Is it wet? Is it dry? Is it gas? So we have basically a Swiss Army knife of techniques available to the users. So then we'll decide which technique is more appropriate to kind of shed some light, pun intended, on the matter.
Dom will also enlighten the team on how the equipment works and how to use it. At the end of the spectrometer is the detector. So light shines through the sample or a control and then hits this detector.
It needs to be cooled. It is cooled with liquid helium. It's also going down to minus 270 degrees. It's basically a thermometer. And as it sees the light, it warms up. And that change in temperature in the detector element is then the intensity that we see on the screen.
It's not a really big space here, but I asked Dom for a tour so I can fully understand the path of the light coming from where it's being made through Dom's domain and then into this detector. Because terahertz light isn't harmful, there's no requirement for radiation shield doors when the beam is on, like in some of the X-ray beamlines. So Dom brings me right to the back of the room.
So we are on one side of the spectrometer, and this is the side that we'll call the upstream side. So we have a wall. Beyond that wall is the storage ring where the electrons are whizzing around. And there's a hole through the wall, and there's a mirror, a set of mirrors that are sitting inside the storage ring, and they are used to steer the beam through the wall into an intermediate vacuum chamber, which has itself a set of mirrors to steer the beam. So this beam is split into two. So we share that source with the microscopy beamline on the other side, which is an infrared microscopy beamline. So they take about half of the beam and we take the other half.
Right, and you can actually see that split here. So there's all of the metal tubes in another vacuum chamber with mirrors on the other side of this partition, kind of leaning into the microscopy side. Okay, so they take half and you take half, which is coming through this series of mirrors and then through this very shiny stainless steel.
Yes, so we have more mirrors on this side of the wall that continue to steer the beam. And we have gate valves that allows us to isolate ourselves from other parts of the beamline. This is just for safety or maintenance needs. If we want to operate and make some changes in between the spectrometer and the storage ring, we can close those gate valves as per need and then do what we need to do to fix things, yes.
Okay, so then the light is coming in here, there's another chamber with mirrors, and then that's where it's getting fed into the large rectangle, which is where the sample's going to be, the cryocooler and the detector. And while the researchers are here on site, so Freddie and Kane and Kitty, your role is, well, A, set them up, which you've just finished doing, and then B, train them on how to use it because they may not have come across it before. And then after that is just keep checking in, if any problems arrive. Are you the first person that they'll call?
Yes, every beamline scientist who inducts and helps the users, we're on support and we're on call. During normal hours, we're on support, so we come down and if there's any issues, they'll talk to us and we'll try to fix it. Hopefully there's none. Then after hours, we're on call until 11. Again, if anything arises, their first port of call would be the operators. Our operators are gold. They are trained in every beamline. This is mind-boggling because for me, I'm already limited to this. I'm learning something else. I'm lost. They know every beamline and they can offer first aid in terms of in the science sense. If there are some issues that they cannot resolve, then they'll give me a call. But before 11 p.m. After that, I'm sleeping.
Kerry and Freddie have come with some materials to test that were made at the Robinson Research Institute at Victoria University of Wellington, where Kerry is in her second year of her PhD.
I'm working with the rare earth nitride research group, growing thin films of these rare earth nitride materials, and I'm specifically investigating their fundamental properties. So as I change their growth conditions, what electronic and magnetic properties am I therefore tuning? And this is to eventually look towards cryogenic magnetic memory applications. So these can go into superconducting computers or quantum computers.
These are kind of the next gen of powerful computers that scientists are investigating now. The rare earth elements are metals on the periodic table that you've probably not heard of. They have names like lanthanum, promethium, terbium, scandium. Handy words for bananagrams or Scrabble, but not really terms we use day to day. And rare earth is a bit of a misnomer, says Curie.
They're not rare, they're actually more abundant than, say, silver and gold. The difference is, I guess, they don't form in big clumps. They're often mixed together in trace amounts in one given area, so they just take a lot of processing to get a pure single element of them.
The neat thing about them is that they have two interesting properties related to conducting electrical charge and magnetism. And this means they might be the key for a new, more stable and energy-efficient way to store data. The field of study of these kind of two-fer materials is called spintronics, which is a cool name. Alongside this thin film of rare earth nitrides, Kerry and Freddie have two other materials with them. And all three can be referred to as quantum materials, says Freddie.
One reason why they're called like this is we don't understand what's going on yet. So this is why we come here and try to understand the mechanisms. And this is why the terahertz beamline here is so amazing, that we can understand what's actually going on a microscopic level in order to understand or to explain the phenomena that we see on a macroscopic level. So we have this material where we see a change in color happening at a certain temperature, which is due to a structural change of the material. Funnily, when you reduce the volume of this material and do the same thing, you don't see this change in color. So the reason why we come here is we do absorption measurements. So we shine light onto our sample and we detect what comes out, and we look out for absorption lines. And so we try to explain those absorption lines, if we see some, with physical models that we already know. And then in the next step, to relate this to the structural or electronic properties of the material.
And the reason for studying them across the massive change in temperature, from 20 degrees to minus 270 degrees Celsius?
These materials, and for a whole range of other materials, you have phase transitions happening. These can be origin of that the structure changes, the magnetic properties change, that the electronic properties change, and these happen at a certain temperature. There are only a few tuning parameters, how to study a sample, application of an electric field, of a magnetic field, temperature, light. And so those are your tuning parameters you want to play around with in order to get as much information out of the system as possible. So it's a bit like this very classical picture of you have an elephant and somebody only looks at the tail and says, oh, it's not an elephant, it's a tail. The other one looks at the feet and says, oh, it's actually a feet. And so you want to have different approaches to get a complete picture of what's going on.
According to the New Zealand Synchrotron Group, this team is one of 113 New Zealand research team visits that have happened over the last 12 months. And the range of things that New Zealand researchers are using this synchrotron light to investigate is just staggering. From investigating underwater volcanoes, looking at new bioplastics, understanding the properties of wool, and characterizing new materials for clean energy. The list goes on and on. But on top of the research science, there's also the other side of young researchers like Kane, like Nicholas, and like Kerry that are getting to go here and to try this for the first time.
So I've been at one before, but not had a dedicated experimental slot, I suppose.
Is it exciting to be here with Beam Time and be...
Yeah, I was really excited to be offered the opportunity to tag along with this Beam Time. I've sort of learned some of the physics behind what's happening, and now I can put that into practice and actually use it, which is pretty cool.
Thanks to Kane Hill, Nicholas Page, Dr. Dom Apadou, Dr. Freddie Lizwa, and Kerry Van Conant. Thanks also to Dr. Emily Parker and Dr. Helen Brand of the Australian Synchrotron. My travel to Melbourne was supported by the New Zealand Synchrotron Group Limited. This episode was produced by me with help from Ellen Rikers and executive producer Liz Garton. It was recorded with the help of Otago Access Radio. Sound engineering was by Phil Bench. You might be interested to know that our friends over on the Country Life podcast did some special stories to celebrate Conservation Week recently. Search for Country Life on your favourite podcast app and check them out. Tēnā koe I whakarongo mai. Thanks so much for listening. Ko klek and kanana ho. Have a great week. Kia pai, the wiki.